Right now, I want to talk about indefinite integrals. But before I get too far into that, I wanted to just kind of think about derivatives for a second. And the reason I wanted to do that is because, again, integration and derivatives are very, very related processes. Remember, the integration is the opposite, is the inverse process of a derivative. So essentially what I'm going to do right now is just take the derivative of these two functions. Now notice I've got f of x, which is 3x plus 2, and I've got g of x, which is 3x minus 7. If I take the derivative of f, then what I should get out is just 3, and that was x to the first, so now it's going to be x to the 0, so there's no more x's. And we're multiplying by the x to the first, the exponent of 1, so 3 times 1 is just 3. That 2 disappears. Now, when I take the derivative of g, I do the same thing and I get the same answer. Now, the question is, were those the same functions to begin with? No. But when I took the derivative, they were. So, here's where indefinite integrals comes in. When we talked about definite integrals, and I'll kind of pick up my red marker real fast. When we were talking about definite integrals, we were integrating from a to b of some function. And what we did was we took the antiderivative of it, and we got f of x, and we evaluated it from a to b by doing f of b minus f of a. Now again, this is a definite integral because it is defined for a to b, that interval. So what makes an indefinite integral special? Well, an indefinite integral is not going to be defined over some bounds. It's just going to be this function with no bounds whatsoever. We're not going to integrate over any bounds. But so what we need to do differently in this case is we're still going to take the antiderivative, and what we're going to do this time that's different is we're going to add a constant. Now notice that's a capital letter C. That's normally the notation that we'll use for, I'm going to use the word constant of integration. That's its name. Okay, so the reason we have the C there is for this exact reason you see up here at the top, is how do I know which function I started with? Well, if all I'm doing is integrating 3 and I just say it's 3x, that's not quite correct because it could be some other number afterwards. It could be a 2, it could be a negative 7. We just don't know. So that C is representing every number that could come next. It's every possible constant term. And so what we're going to call this, down here at the bottom, this f of x plus c, is going to be called a general solution. Now the reason we call it a general solution is because it contains every possible antiderivative. It's a whole family of functions. It is every possible thing whose derivative is f of x. And so that's the thing is, if all I had to do was 3x plus any number, 3x plus any constant at the end, they would all have the same derivative. It would just be 3. And so that's what this is getting at is, again, if I took f of x plus c, its derivative is always going to be f prime of x. So again, this is a general solution. Now I'm going to come back and talk more about general versus the other option is particular solution a little bit later in the video series. And so make sure you just keep this in mind. It is a family of functions. It contains all possible answers. And again, we're talking about the word antiderivative, and make sure you remember it's a capital C. Just in case, sometimes this happens, we take multiple integrals. What we can end up doing is we can put little numbers down here like 1s or 2s to represent different constants. And that's just something we're going to do also later on. Hopefully this helps you guys understand a little bit more about the difference between definite integrals and indefinite integrals.